This talk is about factorisation and differential calculus, and it's based on chapter 22 of the book Vedic Mathematics by Sri Bharati Krishna Tirthaji. That chapter is very short, in fact very brief, consisting of just 4 pages, 4 sides, and it just comes up with 2 things. One is how factors and differentials of polynomials are related, and the other is the detection of repeated factors in polynomials. And he does mention references to Leibniz theorem, Maclaurin's theorem and Taylor's theorem. So this talk is basically in 3 parts, and these are the 3 parts. So we'll begin with factors and differentials of polynomials. And the red text I'm going to show you in this talk is from Tirthaji's book. All the red text is from Tirthaji's book. And so this is the first example he shows in this chapter. X squared plus 3x plus 2 is factorised into x plus 1 and x plus 2, and he calls those A and B. He then works out d1, the first differential, to be 2x plus 3. Clearly, if you differentiate here, you get 2x plus 3, and he shows that that's the sum of the factors. If you add the factors up, you also get 2x plus 3, and so we can abbreviate that to sigma A, sum of the factors. But it's a neat result, and it can be extended. So he goes on to a second example, in which he has this cubic, which factorises like this, x plus 1, x plus 2, x plus 3. And the first differential there, if you differentiate this, is this quadratic expression. How is that related to the factors here? Well, he shows that it's equal to the sum of these 3 quadratics, which are the quadratics obtained by multiplying in pairs. So if we multiply the first pair, we get this. If we multiply the last pair, we get this. And the outer pair, we get this. And that's abbreviated to this, AB plus BC plus AC. That says the sum of the products of pairs of factors. Going on, we can differentiate d1 to get d2, which is 6x plus 12, and that's also related to the factors. 6x plus 12 is twice 3x plus 6, and 3x plus 6 is actually the sum of those 3 factors, a, b, c. So it's twice the sum of the factors, which is expressed like this, or like this. And that 2 is actually 2 factorial, 2 times 1. The third example shows a quartic, which actually factorises into this. So we're interested in how the differentials are connected to these factors. And here are the results. The first differential is found by taking 3 factors at a time and multiplying them and adding up the results. So if you take the first 3, multiply that out, and then you take the last 3 and multiply that out, and then all the other combinations, there are actually 4, then you will get this expression for d1. d2, similarly, if you take a second differential, which is this, is 2 times the sum of the products of the factors taken in pairs. So if you multiply the first 2, the middle 2, the last 2, the first and last, all possible combinations, and add them up and multiply by 2, you will get the second differential. So that's an alternative way of getting the second differential. And the third differential, we can see, comes out to be simply 3 factorial, 3 times 2 times 1, times the sum of the factors. We simply add these up, and we get the 4x plus 10, and then the 6 is the 3 factorial. Well, these are the first 3 examples that Tirthaji shows in the chapter. The first 3, there are only 5 of them anyway. And he then says these examples will suffice to show the internal relationship subsisting between the factors of a polynomial and the successive differentials of that polynomial. but it's not really clear how this might be used, and so I'd like to give some examples that might develop this idea a bit further. So here's the first one. Suppose we're given fx, which is x plus 2 times x plus 5 times x minus 3, to find d1 and d2. So we're not given the cubic, this is actually a cubic here, we're not given the cubic as a cubic, we're given it as the product of three factors. And so our results up here are going to be useful to us because we don't have to multiply the brackets out to get the cubic, we can get the results from the factors themselves. So let's see, it's a cubic, and so that's example 2 here. And we're interested in d1 and d2, and so this is the result for d1, and this is the result for d2. So d1 we know is given by sigma AB, which simply means that we multiply products in pairs and add up. So that means we multiply this product, which is here, this product, which is here, and the two outer ones, which is here. And if we add them up, we get this, and this is d1, and we found it without multiplying out the factors to get the cubic itself. Similarly, d2, we know that's given by factorial 2 sigma a, so all we need to do is to multiply 2 by the sum of the factors. And twice the sum of the factors means twice the sum of these three factors here, which are in the bracket. So that gives us 3x plus 4, which becomes 6x plus 8 when we double. Now, although here there's a little bit of work involved for d1, it's debatable whether it's easier than actually multiplying out the cubic and then differentiating. But here there's definitely a saving because it's much easier to just add up the factors and multiply by 2 than to multiply this out and then differentiate twice. Second example, here we've got x plus alpha, x plus beta, x plus gamma, x plus delta. So it's a quartic, and we're asked for d3. So we're interested in this result here, because this is for a quartic, and this is d3. So 3 factorial sigma a means we simply multiply 3 factorial, or 6, by the sum of the factors, which is that, and simplifies to that. So that's very simple, very quick. Third example, the roots of a cubic are alpha, beta, gamma, find d2. Okay, it's a cubic, so we're into example 2 here, and d2 means we're interested in this result, 2 factorial sigma a. So we simply multiply 2 times the sum of the factors, and the factors are going to be x minus alpha, x minus beta, x minus gamma. So we get the result very easily like that. Now let's move on to the second section, detection of repeated factors, that THG goes into. We may have a function fx given as the product of 3 factors like this. The 3 factors are distinct, meaning they're not repeated, and the zeros or roots are minus 2, minus 5 and plus 3. Here, for gx, we've got a repeated factor because the x plus 2 is multiplied by itself, and so it's repeated. And in this one, hx, we've got x plus 5 to the power 3, which means the x plus 5 is there 3 times. So the question is, how can we use differentiation to detect these repeated factors? And the result which THG uses, but doesn't say and doesn't prove, is this, that if a polynomial has a repeated factor, then that factor will also be a factor of the differential of the polynomial. What that means is, in this case here, which has got a repeated factor, if you were to differentiate g, x plus 2 would be a factor of that. And here, the theorem actually extends further. This is proved in my paper. If you've got a factor to the power 3, then not only will x plus 5 be a factor of h, it'll be a factor of the differential of h and the differential of a differential of h. Anyway, let's take an example. And this is Theorems' first example. It's in red. To factorise this cubic, and this is what he does. He works out dy dx and factorises it. And then he says, judging from the first and last coefficients of e, the given expression, so that's this, we can rule out 3x minus 5 and keep our eyes on x minus 1. So that's okay. X minus 1 is a factor of dy dx. It's also actually a factor of here, of the cubic, and we can prove that by simply putting x equal to 1 in there and showing it comes to 0. Because if x is 1, we get 1 minus 4 plus 5 minus 2, which is 0. 3x minus 5 can be ruled out, as Theorems says, because 3x doesn't divide into x cubed and 5 doesn't divide into 2. So we can rule out 3x minus 5 and keep our eyes on x minus 1. Now the question is, although we've already shown that x minus 1 is a factor of dy dx and of the original expression, we don't know if it's going to be repeated again. So he has to work out the second differential and see if x minus 1 is a factor, which it isn't, and therefore we have x minus 1 squared. And according to the Adyamadhyana Sutra, E is therefore this, because we know we've got x minus 1 squared, and looking at the first and last terms there, that means we've got to have x and minus 2 here to make E. So that's the logic involved in working this out. We differentiate, find the factors, then we have to test if any factor that we've got, which could be a factor of E, is actually a factor of E. And if it is, it's a repeated factor. And then we have to go further to find out how many times it's repeated. Let's look at Theorems' example 4. Here we've got a quartic. So this is what he does. He works out d1, works out d2, and factorises it. Then works out d3 and factorises that as far as possible. Then goes back to d2 and back to d1 and gets e. This is all he gives. It doesn't really explain it very much. And so let me go through. Once the expression is differentiated, we would like to factorise it. But factorising a cubic is not that straightforward, and so he says, well, let's just go on to d2, because quadratics are easier to factorise. And so he factorises it into this. Now it's got x minus 4 and 4x minus 7. 4x minus 7 can be ruled out as a factor of this. The 7 doesn't divide into 64 for a start. At this stage, x minus 4 is a contender to be a repeated factor, not the 4x minus 7. And then Theorems goes on to d3, and we see that the x minus 4 is not a factor there, and so that means that it can't be x minus 4 to the power 4. He then goes back through the differentials. He goes back to d2, which is this, and then x minus 4 is obviously a factor of d2. Is it also a factor of d1? Well, in fact it is, and we can see that if we put x equal to 4 in here, we do get 0, and therefore we know that x minus 4 squared must be a factor, and then we can get the third factor there. Finally, we come to e, the given expression, and by putting x equal to 4 in there, we can show that x minus 4 is a factor, and therefore it must be a cubic factor, and the other factor is easily found. So it's nice the way that we go through the various differentials, d1, d2, d3, and then back to e again, d2, d1, and then e. And I hope this explains the logic which is involved. Moving on to the third part, on the other theorems that Theorems mentions, he starts the chapter, in fact, with this statement here. In this chapter, the relevant sutras, Gunaka Samachaya, etc., which is Sutra 16, dealing with successive differentiations covering Leibniz theorem, Maclaurin's theorem, Taylor's theorem, etc., are given, and a lot of other material which is yet to be studied and decided on by the great mathematicians of the present-day Western world is also given. So if we look at Maclaurin's theorem, which he mentions here, this is the standard expression of it. Fx could be any function of x. It's equal to f naught plus f dash naught x, f double dash naught x squared over 2, and so on. And we see differentiation obviously involved here, because here we get f naught, then we get f dash naught, f double dash naught, differentiations. And we see integration involved as well, because if you imagine a factor of 1 here, then integrating 1 gives x, integrating x gives x squared over 2, integrating x squared over 2 gives x cubed over 6, and so on. So it's a kind of combination of differentiation and integration together. And in fact we can use that for working out series expansions. For example, if we wanted to get a series expansion for e to the 2x, we could apply the theorem. F naught simply means put x equal to naught in here, which is this. And we can get the second term from the first term by differentiating this term as if the 0 was actually a variable, x, like x. So if you differentiate e to the 2x, we get 2e to the 2x. So imagining that the 0 is an x, this is what we would get. So we get this expression here. And then differentiating that would give this, and then again this. So by successive differentiations we get these three terms, and by successive integrations of 1 we get the other terms. And then working that out gives us the answer very quickly. Taylor's theorem also shows a similar pattern. In fact, Maclaurin's theorem is a special case of Taylor's theorem, and you can see here that we got successive differentiations of f a, f dash a, f double dash a, and so on, and successive integrations of 1. 1 with respect to x minus a becomes x minus a squared over 2 factorial, and so on. And in the binomial theorem too, we see the same pattern. If you differentiate the first term, a to the n, you get n a to the n minus 1, and then this one, and so on. And integrating 1 we get b squared over 2, b cubed over 3 factorial, and so on. Our Leibniz theorem, in the introduction, Tetridi says this: it need hardly be pointed out that the well-known rule of differentiation of a product, i.e. that if y equals uv, when u and v are the functions of x, dy dx is v du dx plus u dv dx, and the Gunaka Samachaya Sutras denote, connote, and imply the same mathematical truth. So here we've got a product, uv, and this is the well-known product rule if you want to differentiate a product. And in fact, Leibniz theorem is one which allows you to differentiate and keep on differentiating as many times as you like. So suppose, to take an example, you wanted the differential of x to the 5th multiplied by e to the 2x. So that's a product. And if we write the two parts of the product like this, x to the 5th and e to the 2x, and write the differentials next to them like that, then the differential of the product is found by simply cross-multiplying and adding. So the first differential is x to the 5th times 2e to the 2x, which is here, plus, going this way, 5x to the 4th times e to the 2x, which is here. And if we extend this, we want the second differential now of the same product. You will see that the values here in the first two columns are the same as before, but we differentiate again to get 20x cubed here and 4e to the 2x here. And then the answer is simply found by cross-multiplying 3 times like that and adding up. And so this is an application of the vertically and crosswise sutra. So D1 is the first product there, which is on the first line. The second product, the vertical product, on the second line here, and the third product here. And we've got this extra factor of 2 in there, which actually comes from Pascal's triangle. In fact, the three terms here are multiplied by the 1, 2, 1 in Pascal's triangle there. And in fact, these terms here were multiplied by the 1 and the 1 there. So this makes it very easy to find any differential of a product. If you want the third product, we would go up to the third differential. First, second, third differential, and the same here. And then we'd use this nice pattern to add up the products of pairs, and we get this, in which the four parts of this are multiplied by 1, 3, 3, 1, which are the coefficients in the fourth row of Pascal's triangle. Leibniz's theorem is generally expressed like this, which is quite complicated and does not show the underlying vertical and crosswise pattern that has come out here. So I hope that these comments have clarified the contents of chapter 22 of Titchege's book. And just to sum up, we've seen how Titchege's relationships between the factors of a polynomial and the successive differentials can be used to simplify differentiating polynomials given in factor form. And then Titchege's method of detecting repeated factors in the polynomial has been explained and clarified. And then the comments about Leibniz, Maclaurin and Taylor's theorems have been explained too. Thank you.